Could you define that? I'm just curious. Like, you think you could? Cool, let's go for it. Let's define it. What does it mean? Let me draw a freaking picture even, huh? Make life good.
Like, as some sequence of points x of n, or x of n approaches x naught, f of x of n approaches l.
Okay, cool. So we definitely have had this limit. So if I take an x of n, a sequence converging to this x naught, then f of x of n converges to x naught. But we haven't talked about it without a sequence reference, I think. I think that's true. Hi. So let's actually talk about that. If I put this here, what would that be saying? What is that a statement? What does that mean?
As x approaches x naught, f of x approaches f of x naught.
Cool. Yeah. What does it imply about the function f?
That it's continuous.
Continuous at x naught. Right. So this is continuous at x naught. That's exactly right, because what it's saying is that no matter, so this is a statement that's a little more general than the sequence one. This is saying that no matter how I approach this, it's kind of abandoning the language of sequences and saying that you tell me how close you want to get to this L value, and I'll give you an input window around that point that doesn't include the center, because limits aren't about the center, so that when you tell me how close you want to be up here, I can always find a closeness response down here, so it's that call and response game that gets the graph inside there. Whereas something like this, if I had, and then it just jumped up like that, and this was x naught, whatever I claim to be the limit, there's going to be values that spill out here. So these guys here, no matter how close I get to x naught on the left, I'm going to be below that little epsilon 2. And then to the right, I'm actually in it, but not everything is in there. So this definition right here is a definition of continuity. What is the definition of continuity? Can you write that out? The epsilon delta version. Yeah, there you go. Let's try that. It's okay. It's like karma free. No pressure. Oh my God, this board is so fucked already. Anybody got it for me? Almost.
Start for all epsilon.
There you go. That's a hell of a good way to start any real analysis definition. Absolutely. That's how you shoot for partial credit, right? Perfect. So what else do we need?
You need a there exists delta.
Oh, hell yeah.
It goes in.
Yeah. Got call, response. What is it saying then? Such that
Such that the absolute value of x minus x naught being less than delta implies that the absolute value of f of x minus f of x naught is less than epsilon.
Yeah, beautiful. Tell me how close you want to get this. I'll tell you how close you have to be to the input to get that close. Now there's one little subtlety here. Notice that on this side, I can have x equals x naught. So there's a couple things hidden in this definition. First off is this call and response thing. The second thing is that x can equal x naught here, And f of x naught is defined. So here, notice that f of x naught is defined because I'm writing it right there. I don't have that L like I did for the limit. I know what the limit is, and it's the value of this function there. So f of x is defined, and we can have x equal x naught. In fact, we have to actually get that value. When I put x equals x naught, this turns into a 0 over here, the lowest that could possibly be. So, yo, go ahead.
I think I might be missing something, but if you set x equal to x naught, wouldn't that mean that delta is 0?
So the delta, so you tell me, you say I want epsilon to equal 1/10, and then I say, well, there's this delta that is 1/5, and I put that here. So as long as you're within 1/5 of this point,
Okay. Yeah, I
but this would include that.
Yeah.
Does that make sense?
I see.
Yeah, that's cool, awesome. Good questions. Any other things to like clear that up? So remember what when we talked about this, there was 3 things. The first is that the limit as x approaches x naught of f of a naught exists. That limit actually exists. And then the second thing was that f of x naught is defined. And then the third thing was that limit as x goes to x naught of f of x actually equals that value right there. So let's look and see where we have these various things. So first off, f of x naught is defined. It's encoded by me writing it here. The fact that I wrote it means I can write it. So this is in that definition. Then there's this part right here, that the limit exists. And remember, the limit's not about what happens at the point. The limit's about what happens nearby the point. So the limit exists part, this is most of the definition. This is, in fact, for all epsilon greater than 0, there exists the delta greater than 0 such that, now watch how I'm going to alter the definition, such that 0 less than x minus x naught less than delta implies f of x minus f of x naught is less than epsilon. So this part right here, just saying that that limit exists and equals f of x naught, so these 2 things, I guess, really together are said in this statement. So the limit definition is just like the continuity definition, except we just allow x to equal x naught. Notice how that keeps x from equaling x naught, because you have to be greater than 0. As soon as I remove that, this becomes the continuity definition. So I just wanted to point out that this right here is another way to talk about the limit of a function. And this function, that limit's going to equal f of x naught if the function's continuous there, but it's going to equal L if, and which is not equal to f of x naught if not continuous. Or this limit won't exist at all. So there's lots of ways it can go wrong. So how do I do, let's talk about this and just go back to some basic calc. How do I do this? How do I take that limit? Well, what's the first thing I always try? Just like plug, we always try the plug-in. So notice that this function is not continuous at x equals 2. It's not even defined at x equals 2. So not defined at x equals 2. So it can't be continuous there. But I can try the plug and chug, and when I do the plug, I get 0 over 0. So then, now I heard someone say something about L'Hopital's rule. Is there maybe an even simpler route that doesn't require calculus? Does anything factor?
Factor.
Yeah, I'm hearing not confident responses. Yes. So what was that? He was right.
Difference of squares.
Difference of squares, so how do I factor the top?
X minus 2 and x plus 2.
Beautiful. So notice that that actually cancels. And now I've got limit as x goes to 2 of x plus 2. And now I can plug and chug and I get 4. So this is kind of, this function is identical. So let's write this up. X squared minus 4 over x minus 2 equals x plus 2 if x is not equal to positive 2. So it basically looks like that line right there, x plus 2, except at 2, where it's got a little hole. So this is x squared minus 4 over x minus 2. That's how we take that limit. I've got a couple other examples here I just want to look at, because I just want to make sure we have touched upon these things. How about this one? Could you do me a favor and give me a definition of this? What do you think the definition of that is? So take a minute, write a response call definition. It might be similar to the epsilon delta, it might not be. Right back. Anybody got a definition for me? If we're wrong, it's no big deal. You give it a shot, Christian?
Sure, I got something.
I like it.
Is that at x naught, for any delta greater than 0, there exists an epsilon greater than 0, such that the absolute value of x minus x naught being greater or less than delta is true alongside the fact that the absolute value of f of x minus f of x naught would be greater than or equal to epsilon.
Okay, we're headed definitely in the right direction. I like this. But what's f of x naught?
It's infinity.
So this idea here is great. This is awesome. We're getting there. We're pretty close.
Yeah.
Couple of things though. I think we want to reverse we want to have a for all epsilon because
Okay.
I want it right. So I want the epsilon to be here, and then the delta is always the response variable. It's always you give me this, I'll give you that.
Yeah, I guess I was kind of just thinking about like the negation of that statement, right?
Were you negating the?
Like the continuity statement.
Yeah, it's not quite. I see where you're going with that, but it's not quite a negation of continuity. It's got its own kind of magic going on. But that was like honestly, you got pretty damn close.
Fair enough.
What could I do here? So let's think about what we want to happen. So we got x naught, and we're saying plus infinity. So let's say that it must look something like this. Because first off, I'm talking about the limit as we approach x naught. That means I can come in on either side. And no matter how I come in, I shoot up to infinity. So the graph kind of looks like that. So for all epsilon greater than 0, where would be, I can't go up here to infinity and put a little epsilon tube around infinity. That ain't gonna work. But this gives us a hint. This is perfect. This is the great thing. Now we don't have this guy, right? And we're going to plus infinity, so we can assume that eventually we'll be positive. I don't need absolute values. But if I just tweak it like this, then, and I also make sure I can't get to x naught because I don't want to allow x to equal x naught. Now I've got the perfect definition. Now, we're used to epsilon being a tiny thing, so if that is unnerving, in a way, this can make our brains feel a little better if I just put an m here. So, what does it mean to go to infinity? It means you tell me how big you want the output to get. You tell me how big you want this output to get, and I'll find a little window around that input that gets me above that. So no matter how high you make it, I can find a response that's a little closer and gets me above that cutoff. Does that make sense?
Yeah.
Does that make some sense? So let me ask you this, can you do this one? Man, they made this board like shitty over the weekend. We never have this kind. This is like Clark board performance. Right, Calc 3 friends? This is like garbage board. So how would you write this? Let's just do some practice with this. X goes to x naught, f of x equals negative infinity. Let's just warm up. I'm gonna tweak it just a little bit. Oh, by the way, y'all, you missed an amazing talk by our Mr. Cormick here. Dude kicked ass at the conference. Amazing talk. Made us proud here at Regis. And like almost the entire Regis math department was there to see it. 75% of us. So Camila, do you have something you feel?
Kinda.
Well, let's try it.
So for every, I used M again.
I like it.
Greater than 0, there exists a delta greater than 0.
Oh, so for all m greater than 0. Okay.
Yeah.
Yep. There exists a delta greater than 0.
Such that, and then I did 0 is less than x minus x naught.
Yeah. Good stuff.
Is less than delta.
Yeah.
And then I flipped it. So it implies that m is less than or equal to f of x.
Okay. Cool. So let's check this out.
Or less.
Is it, oh, sorry. Is this what you said? Less than or
Yeah,
equal? Okay.
No, less than.
Unless you can, yeah, I could go either way. It's all good. So let's see. So I give you, so you're saying a positive m here. So for your definition, all the m's have to be positive. Now let me take a look at an example here really quick. Here's a function. Totally let's say it's -2 right there. You're saying for every m greater than 0, so here's my m, bigger than 0. There exists some response so that f of x is always above that m. Is that true here? No, because this is all below, right? What do we need to tweak here? So let's look at this picture. Let's work together. We want to be able to set an m that I can always fall below, right? You give me an m and I show you that I can get close enough to this to fall below it. So how can we tweak? Your definition's almost there. It's pretty close. What can we do to tweak it? Yeah, so definitely let's get that, let that m be negative. Yeah, I love it. There exists some negative m. Awesome. And do we want the f to be above this line or below that line? So what am I saying? We want it to always be, you give me a cutoff and we can always get close enough that everything is under that line. And that means that I can always keep janking this thing closer and closer to negative infinity by getting closer. So we just make this little tweak here and we say that m bigger than f of x, that f of x falls below my cutoff. Does that make sense? Yeah, cool. Good work. All right, let's, this is fun. This is a good game and I feel like it's making us stronger to practice this. So how about this one? Let's try this one. This is you're gonna tweak. So maybe think of what we've done, but think outside the box. And a picture always helps. So we're looking at horizontal asymptote. Right? That's the kind of thing we're thinking about. How do we write that in a formal way? Starting to like
Yeah.
see how it all kind of, yeah, that's what I just wanted to do, get us to being able to kind of work with. How's it going? What you got?
I don't know.
Okay, so let's see here, okay. So what's M? Oh, so you're saying you can hit that, okay, that's, we might not be continuous at a point, so this is assuming you can actually hit that value that you're setting.
Okay.
So let's think about this. We want to talk about getting closer to that L that I've got there, right? And so I want to somehow express that you tell me how close you want to get to L. I can tell you how far out to the right you need to go to get that close. Do you see what I'm saying? So how could we write, so how can we talk about closeness to the value L? Think about how we normally talk about output values. What's the Greek letter we use for response?
Delta.
So that's, we could use delta, but we usually use epsilon on that output side. Does that make sense? So you give me an epsilon, and I can show you a place on the x-axis where from that point to the right, the graph is within epsilon of L.
Okay, so maybe
Yeah.
probably like the opposite of F of X minus L.
Yeah, that's what we're getting close. So that's the thing that we're gonna make as close as we want.
Okay.
So so the call is gonna be an epsilon, right? So let's kind of, you can all check yourselves here. This is back to epsilon tubes, because we're talking about getting close on the horizontal strip kind of scenario. So you tell me how close you want to get to that, and maybe you want to be this close right here. So let's make a super fine thing. No matter how close you want me to get to that output, I can find a place, M or N or whatever, I think Christian used N, but I can find a place on this x-axis where from everywhere out, the function falls that close to the line L. So what we're looking for here is, for all epsilon greater than 0, there exists an M or an N greater than 0, so that if X is bigger than M, f of X minus L is less than epsilon. And I think that's exactly what you had. How do we feel about that? Yeah? Cool. All right, I just wanted to that was actually more than I thought we would do on that, but it's like started feeling like we need to do this to like just pull some things together, especially writing analysis definitions. But we're actually kind of coming to a new topic, pulling together lots of things from this semester in kind of our final push to understand power series. And so this is going to feel a lot like Calc 2 in a way, but you know, as with this class, way more detailed, way more intense than Calc 2. But let's introduce power series, or reacquaint ourselves with power series. So there's two ways. So first off, I'm going to say that A sub n is a sequence of real numbers. Already, if I said this in Calc 2, this would just disturb people. Sequence of real numbers. But you're all good on that. It's just an infinite list. Infinite lists don't stress us out. They get us very stoked. Oh my God, you guys, I started taking this supplement over the weekend, and I actually like feel not tired for the first time in like months. Have you ever heard of methamphetamine? No, I'm just kidding. No, no, it's not. It's this precursor. It's this precursor to some like this stuff NAD in your body, and you lose it as you get old. And I'm old, so I'm taking this stuff that I don't know. It might be completely psychosomatic, but I like seriously haven't felt this energized and awake in a long time. Only 2 days. So, that's good, that's on the recording there. At least I cleaned it up. So, I've got a sequence of real numbers. What do I want to say? How do I want to say that? Oh, then the sum, a sub n, x to the n goes from 0 to infinity, or sum a sub n, x minus x naught to the n, is a power series. This one, this is called the center. X naught is the center of the series. What's the center here? What value of x naught would give us this series? Yeah, this is centered at 0. See, if x naught is 0, you just get this guy over here. So this is centered at 0. And we're going to probably just stick to that for a while because the other stuff is just kind of shifting where the center is. So there are, notice this is a function of x. This value of the series changes, so the value changes depending on the input, the value of x. So we've got something here that seems like a function. Let's actually write out what this guy looks like right here. So this guy is a sub 0 times x to the 0 plus a1 x to the first, a2 x squared, a3 x cubed plus on up the line. Is this all making sense? I hope so. We kind of did series before, so this shouldn't be too shocking that this is it. Every series is defined at its center. So at x equals 0, this is just equal to a naught. At x equals x naught over there, what does this series look like? Let's write this guy out. This is a naught times this to the 0 plus a1 x minus x naught to the first, a1 times x minus x naught squared. So at x equals x naught, it's just equal to a naught. All these series, every power series exists at its center. So let's just make a little note. So every power series is defined at its center. It's just that constant term right there. It's when x starts being non-zero and we get an infinite series here that things become tricky. Does it converge or diverge? So one of the questions we're going to get is, given a power series like this, what values of x is it defined for? It's a question. This is the big question we want to ask, and we'll ask this week. What values, for what values of x does this series converge? And once we have that, then we can treat it like a function at those points. You've got an input and you've got an output. The output's very fancy because it's an infinite series, but that's okay, that doesn't stress us out. So there's three answers we can come up with for this. And it seems like there should be a lot more, but there's only three. Three possibilities. The first is that the series only converges at its center. No other value can possibly work. As soon as x is non-zero, no matter how tiny it is, the thing blows up or just never converges. It's like 1 minus 1 plus 1 minus 1. So that's the kind of possibility we have. The series Second possibility is the series converges for all x values. For every single real number x, you can plug in there, no problem. It's a finite sum, converges. And then the third possibility, and they're all interesting in their own right, but this is one that involves the most work. There is a constant r greater than 0, so that the series converges for all x within r units of the center. So i.e., we get this thing called the interval of convergence. And it's going to look like this. It's basically, here's your center. This is the real number line. Here's your center. Here's the center plus r. Here's the center minus r. And I'm going to leave those endpoints out for now. Put little open circles on them if you're drawing this picture. So in other words, I'm trying to say this interval, this open interval, and it might, note I left this open, but it's possible that both endpoints, neither or just one or the other, can be included. So put a little note here, note, either, neither, or both endpoints might be included. And that's, things get very tedious then at this point. I don't know if you remember in Calc 2 at the end, like testing, finding intervals of convergence and testing the endpoints. Does that sound like something you've ever done in your life? No? Some of us yes, some of us no. Okay, cool, well you're gonna get to do it. You're gonna get to do it in its full glory. Welcome to Calc 2. Just gave a talk at a math conference, gonna learn some Calc 2 today. Nice. All right. And then here, I would actually put here, also put a little star. The series diverges if we're outside that range. Diverges outside the interval. In other words, when x minus x naught is bigger than r. You know, that was like the first math conference I've been to that I actually understood like every talk I went to. I got kind of, like some of them I'm like, okay, I don't care about this detail you're telling me, but I get what we're doing. Like, given enough time, I could do this. You're a crazy person for doing it. All right, so let's take a look. Let's see. Oh, yeah, I want to do a theorem that helps us find all this stuff. So how to find which of those scenarios we're in, how to find R, and then what to do after that. Okay, the board's actually starting to get better, which is kind of weird. Take it. All right, so this is theorem 23.1 in our book, but it's just like a fact of life given, and I'm actually altering it a little bit, given this. Let's actually do the general version, x naught to the n. We're gonna let beta be the lim sup of the coefficients raised to the 1 over n. So let beta equal the lim sup of the a sub n's, coefficients in front of there, magnitude of those, to the 1 over nth power. This is like the root test. This is essentially what you would do for the root test for convergence. And if that was less than 1, then this series would converge. And then we're gonna let R equal 1 over beta if beta is not 0. And beta is not infinity. So if beta equals 0, then that means your radius of convergence is infinity. 1 over 0, think of that as infinity, kind of the cheesy way of thinking about that. And if beta equals infinity, then R equals 0. This means only converges at the center. Can't move away. This means it converges for all real numbers. And then this is the restricted case here. So in this case, if beta is between 0 and infinity, then R is the radius of convergence, and the series converges for, and converges absolutely. Good Lord, my handwriting's getting bad now. Absolutely for x between x naught plus r and x naught minus r. So this is r is a finite value, like 3 or something like that. And then you add it to the center, you subtract it from the center, and you're good in all those. The endpoints must be tested. And then either included, so that's a separate thing, separately. We'll talk about how to do that. All right, now we're just gonna have fun. I think for the rest of the hour, we're gonna think about series. And let's get some famous ones knocked out. Examples. Sum n equals 0 to infinity, 1 over n factorial, x to the n. Let me let you get caught up. Some folks still looking on the left side of the board. That word is absolutely. Anybody recognize that series? What's another way to say that series? It's a famous one. Looks like this. Really beautiful, right? It's very, very rhythmic. It's all synced up. What's that series? It is a Taylor series. All right, good. We're cracking open the old eggs. Yeah, this is good. Absolutely, yes, sir. Taylor series, Maclaurin series means you're centered at 0. Taylor series is the general, can be any center, but you're absolutely right. Let's just take a look here. What's the if just imagine you could take the derivative of this. What's the derivative of that? I just want to see if I can get you to recognize it. What's that?
Doesn't it just keep shifting to the left, kind of?
Yeah, derivative of 1 is 0, right? So it goes to 0, derivative of x, 1. When you take the derivative of this, the 2 comes out in front, cancels with the 2 in the factorial in the bottom, turns into an x. 3 comes out front, that becomes an x squared. And then that 3 cancels with the 3 and the 3 factorial, and I get 2 factorial. And then x cubed, 3. So its derivative is itself. What function is its own derivative? Yes. This is e to the x. Just a little reminder. And what values is e to the x defined for? Are there any restrictions on the x? Is there anything you can't put in there for x? It's good. So I should expect, if I do this stuff over here, I should expect to get the r's infinity case. Because this thing is defined for everything. So if this shit works, that's what I better get. In fact, I better get beta equals 0. I need to get that the lim sup of those terms is equal to 0. So the a sub n here is just this. That's the a sub n, it's 1 over n factorial, it's the coefficients. And I'm actually gonna write up I'm gonna put this up because now I want this other form. So this is good, you can also do this, and let's do this. Lim sup of ratio of subsequent terms as well. That's also gonna be the same thing. It gives you the same value. This is root test, this is ratio test from those anyway. It's just gonna make life so good over here. So this I would use if the a sub n's have a variable exponent, have an exponent that changes with n. Depends on n. And then I would probably use this one everywhere else. Every other case. Because once you got that exponent that depends on n, this will undo that n, and it just makes life really chill. So over here, we're gonna go to our test, we're gonna say beta equals lim sup of, I'm gonna rewrite this one more time for you, because this thing right here is a sub n plus 1 times 1 over a sub n. I just want to note that it's the reciprocal times the n replaced with n plus 1. So let's write that out. This is a to the n plus 1 times 1 over a sub n. And 1 over our a sub n plus 1 is what? What's this?
1 over n plus 1 factorial.
Yeah, beautiful. Just replace the n with n plus 1. And then what's 1 over a sub n?
N factorial.
Thank you. So, yeah. And see how nice that's going to work? What actually am I left with afterwards? What cancels? Just get 1 over, because this thing here is n factorial times n plus 1 in the bottom. It's just an extra factor. So it's lim sup of 1 over n plus 1. And what is that lim sup? If the limit exists, the lim sup is the same thing as the limit. What's the limit as n goes to infinity? 0. So beta equals 0. Beta equals 0, the radius is infinite. Since beta equals 0, the radius of convergence is infinity, and this series converges for all real x. And it better, because it's e. It needs to be good. It needs to treat us well. Is there any questions on that? No, we're kind of just going to do some of these for the rest of the hour. I'm going to give you this next one and leave it to you for a few minutes. So find the interval of convergence, the IOC, for sum x to the n equals 0 to infinity. Ooh, let's look at what it looks like. It's 1 plus x squared plus x cubed Nice. Let's use this test to find the interval of convergence. Where is your center, by the way? Just before we move on, let's make sure we got our ducks in a row. 0. Center. Oh, what were you saying?
I was gonna say 1 because like n equals.
Those are the a sub n's, definitely. So a sub n is always 1, but the center, because it's not x minus anything else. So like if this were centered at 1, it would look like this, Christian.
Yeah.
Does that make sense?
Yep. Yeah.
Okay.
No. So this isn't the coefficient. These are just the constants in front.
Yeah, it's actually much easier, right? They're just kind of not changing. It's looking good, Cecil.
So one thing, don't confuse the a sub n's with the terms themselves. So these are just the numbers in front of the powers of x. So it's 1, 1x. So a sub 1 is 1, a sub 2 is 1, a sub 3 is 1. So this is based off of the coefficients on the variable part. There won't actually be an x in there. Does that make sense?
Okay, cool. Nice, beautiful, awesome. Is that frightening?
Yeah.
No, you got it. What's 1 to any power? Yeah. It looks wicked,
Yeah.
but it's yeah.
Yeah.
So I definitely saw a couple folks using the wrong things for their coefficients. Coefficients are 1 for every single term. This thing, when we find beta, that is not involving, there's no variable in that. This should just be n's or constants like we have here. But there's no x's in this lim soup of, and then here I guess we could, so I'm gonna go with what Camila was using. She was using this one, totally cool, works out, get same answer either way. So that's lim soup of 1 to the 1 over n, and 1 to any power is 1. So beta is 1, it's finite, so I know that I'm going to have some interval of convergence that only allows me to move 1 over beta away. So that's just 1 again. So the center is 0, and we can move out as far as 1 unit that way and 1 unit that way. So my interval of convergence is the open interval minus 1 to 1. Now we need to test the endpoints. So we're going to plug each endpoint into the series and see what it looks like. So could you do that for me real quick, please? Could you plug in, let x equal -1, what series do you get? Let x equal +1, what series do you get? And do either of those converge? I'm going to bring up Desmos. Making a cool thing for us to look at here. Okay. Does this look like where we're headed? Series look like this? Does this series converge? Why not? Yeah, I agree. Why not, Liv? I agree.
It just keeps oscillating between 1 and -1.
Yeah, it doesn't die out. Terms don't die out. Terms have to, if the terms don't die out, the series diverges. So this diverges by, I think we called it the nth term test or the divergence test. Same thing with this. This is literally a bunch of ones added up forever. So this one also, they both diverge. So the endpoints aren't included, and our final conclusion is the interval of convergence. It's just that range. Let's take a look at why. What kind of a series is this? So we had, what are the kinds we know? It's, what's that?
Harmonic. Or was it?
Not that one. No, it's not 1 plus 1 over n. It's not the 1 over n sum.
Oh,
It's power series. Geometric. Do we see it's geometric? Because to multiply from term to term, my common ratio is x. From here to here I get x, from here to here I get x. What do I need for a geometric series to converge? What has to be true about R?
It has to be less than 1.
Has to be less than 1. Well, what's R here? It's just x. So this is a geometric series. It only converges if x is between 1 and minus 1. We just came there a whole different way. We didn't think about the geometric series part. If it does converge, what does it converge to? How do we find the sum if we converge of a geometric series? What's the formula? What's the gain? What goes on top? I'll help you out. First term, 1 minus r. First term is 1. Common ratio is x. So this is this. And we can see here that x can't equal 1 either, because I have a giant asymptote. Let's take a look at a cool little Desmos thing I pulled together for us. Cool. So I actually entered the series. You can, if you just type the word sum in Desmos, it'll start to create a sum for you. And I created a sum where the upper limit was a slider. So I can change that to the number of terms. When k is 0, my first term, it's just my first term, and it's 1. So it's just constantly 1, right? When k is 0, we just have, the function is 1. And then when I let k equal 1, it turns into 1 plus x. It looks like that. This is the line, the slope 1, y-intercept 1. And then here's the quadratic version. I'm gonna back out a little bit. I want you to kind of watch what happens here as we take more and more terms. Do you see how part of it's stabilizing on the right? And it's that left-hand tail. Notice how it's moving out a little bit more every time I move deeper into the series. But this stuff on the right seems like it's pretty stable. And it seems like it's actually starting to go look like the series 1 over x. Look at how actually perfect it meshes up with it, just right here. And if I went out further, if I could go out further, so I could set k to 100, then I'm going to go out a little further. It starts to really slow down. Let's take a look at 200 and see what happens. I mean, I can barely, it barely is changing at this point. That's why you need the infinite series to get yourself all the way out to here. But actually, maybe we can't get any further. I guess we just probably, it looks like it's settling on -1, right? That the x value where things actually sync up is between +1 and -1, and I'm just getting closer and closer to that -1 there. Yeah, I guess I can never actually get past left of -1. Let's just try it. I don't even know if the precision of the computer can work that well. Yeah, so there we can see the convergence interval a little bit better. Anyway, just kind of a cool visualization of what we were doing here. Let's take a look at another one. Got one for you here. How about this guy? Please find the interval of convergence for this series. Sum n factorial x to the n. Very similar to the first one we had, except it's not 1 over n this time. where's it converge? Only at the center. Yeah, awesome. Okay, I've seen some nods of agreement on that. Let's go through it. So our a sub n's, the n factorials, and we are going to set beta, and our center is 0. And beta is the lim sup. And so for this one, I would use the ratio version just because factorials cancel nicely. So that was the way to go. If you had this, you were probably in a lot of pain. Because that's really, that's just a painful, horrible thing to have to think about. But this is lovely because this is lim sup of 1 over n plus 1 quantity factorial. And this is just, oh wait, sorry, no, gotta ask backwards. That's n plus 1 factorial. This guy is 1 over n factorial. When they cancel, I'm just left with n plus 1. And that's plus infinity. And so when you think about the radius being 1 over beta, it's just 1 over infinity, it's 0. Can't move in the slightest. This converges exactly one spot, and it's when the whole thing is mostly dead. So it converges only at x equals 0. Cool, good work. Any questions on that at all? No? All right, I'm gonna kind of just ease us into what we're gonna talk about on Wednesday. And why we're even talking about this stuff and how's it going to tie in with everything that we've seen so far. So here's a question. We've kind of seen, we've gotten the sense that these things can be treated as functions. Let's get my precise verbiage out here. So if we have f of x is this power series, and we'll just use around 0. These results all translate, you just translate everything. And we know that this converges for x less than r units away from its center. Is f continuous? Is f differentiable? This one we probably won't get to answer, but these are great questions to answer, to ask ourselves. And I want to give you an example to kind of like just leave us with this like, oh shit, even simple things can be pretty terrible. So first off, this thing here is a sequence of functions. So to answer this, we view this series as the limit of a sequence of functions. So now things are getting very deep because instead of sequences of points, we're going to have sequences of functions. And this is like just starting to enter an area called functional analysis, where instead of points, your objects are functions. Instead of just working with R, Rn, the things that you're talking about are just functions. This was actually my specialty, so this is near and dear to my heart. And I like to think of it as infinite dimensional calculus, because a function can be thought of as an infinite dimensional vector. We'll get into, maybe I'll talk about that on Wednesday. Some of you probably heard me go off on that, but it's worth going off on many times in a lifetime. So to answer this, we view this as the limit of a sequence of functions, i.e. f sub n of x equals sum. And here I'm going to change the index to k, 0 to k, or k equals 0 to n, a sub k x to the k. So in other words, it's a sub 0 plus a1 x plus a2 x squared plus, and then it truncates here at a sub n x to the n. So it's just like a polynomial, right? It's literally just every step of the way, I'm just looking at a sequence of polynomials, and I'm wondering, where does this end up? If we keep expanding the polynomial, how does this thing behave? And let's look at a confounding example, the simplest example we can have. So let's consider a sequence of functions that just looks like that. Just powers of x. And let's look at it on a restricted domain 0 to 1. So let's think about what we got here. So f1 is just the function x. f2 is the function x squared. f3 is the function x cubed. And so on down the way. Just higher and higher powers of x going on there. Yeah, I don't, it will be too much to get decimals going on this right now. But let's just kind of think of it on 0 to 1. So we're gonna come over here. First function is x. So there's f1, here's f2. f3 is underneath that, that's the cubic. f to the fourth, now I want to kind of argue this right in here. These numbers in here, these are numbers between 0, this is 1, but these are fractions. When you take a fraction between 0 and 1 and raise it to higher and higher powers, what happens? Smaller and smaller. These are like 0.9, 0.9 times 0.9, 0.9 times 0.99, 0.9. You're just shrinking things down. So what happens is that if you look at a particular x value inside here, and it's between 0 and 1, but not at 1, that location shrinks to 0. But what happens at 1? What is 1 to the nth? It's just 1. So what happens is, in the limit, as we let this thing go to infinity, the end result is a function that's 0 all the way over to 1, but at 1, it jumps up to 1. So the limit is actually this discontinuous thing. But these are the simplest continuous functions in the world, right? So how the hell could we ever hope to have a continuous function as our limit when even x to the n doesn't work? Well, that's what we're going to talk about on Wednesday. Thanks. Calc 3, friend, I left my notes at home. I'm going to have to crank a lecture together between now and then. We were just going to work problems today, so I think I got it.
Shouldn't be too bad.
What's that?
Shouldn't be too bad, though.
Not at all. Not at all.